right? So you all did come forth with, in different groups, all of the keywords that I needed for today's discussion. So excellent work. When we talk about energy, I want you in chemistry to think about energy as the agent of change. Whenever matter is changing in some way, then energy has to be involved in that change. And then that's why we talk about energy. We're not going to study the energy itself, but we're interested in how energy relates to the changes in matter. And so we have to have at least some basic functional knowledge of energy. And that's what we're starting with today, although we will explore it again later on. If you go on to physics, there's a more detailed and specific definition of energy. And physics is the course where you actually do study energy itself in great detail. But chemistry is the science of matter. And so we're only interested in how energy can change matter. Specifically, we're going to talk about two ways that energy can change matter. And then if we get a chance, as I mentioned, we'll talk about a third way when we get to nuclear chemistry at the end of the year. We're going to touch on both of these ways in this unit, but the second one is the most important focus of this current unit, and we'll come back to this first one later on. But energy can change the composition of matter. We can actually transform matter from one identity to another. Energy is involved in creating or destroying, or not destroying, but creating or breaking apart compounds, right? And so if I want to turn elements into a compound, energy is going to be involved. And if I want to separate a compound into its elements, then energy is going to be involved. Any kind of transformation of the composition or the identity of the material is going to involve energy. I gave you a couple examples of that last week, so I'll recall one of those. Hydrogen and oxygen, for example. If I have hydrogen atoms and oxygen atoms and I just dump them in a container, guess what I have? Hydrogen atoms and oxygen atoms in a container. That's what I have. Because it doesn't just spontaneously create water. Without energy, the hydrogen and the oxygen will not combine together and rearrange their atoms into a new structure, which is the water molecule. It takes energy, and in this case, it takes heat, or thermal energy is the formal term for that. You have to add heat to the hydrogen and oxygen, and then when that happens, it actually explodes because hydrogen is flammable, but water is produced in the process. So the energy is required to transform the separate elements into the compound. Same thing in the other direction, right? If I have water and I want to separate it into hydrogen and oxygen, I can't just like filter them out or boil it and expect them, you know, one of them to boil away or anything like that. It takes electricity, right? So electricity has to be passed through the water to separate the hydrogen and oxygen into their separate forms out of the water molecule. And of course, the water is a different substance than the hydrogen or the oxygen. And that's very important. When we talk about energy transforming matter, it can actually change the composition. We can change from one substance with its own unique identity to another substance with a different identity and a different set of properties. All right, that's the first bullet point here. That we'll touch on at the end of this unit, but we'll spend an extensive amount of time on that later on in the course, particularly in second semester. Most of this unit, we're going to be talking about energy changing the state of matter, right? And of course, all of you have experienced this if you've boiled water or if you've seen an ice cube melt. It takes energy, usually heat, thermal energy, in order to change from one state to another. And remember that energy doesn't always have to be added to create a change. Sometimes energy can be removed from something, right? So we think of adding energy as heating it up, and we think of removing energy as cooling it down. But either way, when we change the energy, we can actually change the state of the matter. When I say state, I mean solid, liquid, and gas. Again, plasma does exist, but it's something that we're not going to talk about right now because it's a more complex form, more complex state of matter. So as I mentioned, energy is the ability to change. And there, as you all identified, there are two broad categories of energy: kinetic energy and potential energy. And all the types of energy or forms of energy that you talked about actually fall into those categories. So for example, electrical energy moving through a wire is kinetic energy, right? On the other hand, electrical energy stored in a battery is potential energy. right? And so kinetic and potential has to do with whether the energy is being actively used to change something, or whether the energy is being stored and nothing is actually changing at that point, right? And so anytime something is actively changing, then some form of kinetic energy is involved. That could be as simple as just the object itself is moving, which means it's changing location. If something is changing, then energy is involved. I push something and it moves. It can be much more complex than that, and we'll see a little bit of that complexity as we go through this unit. Kinetic energy is easier to understand because you can witness the change. You can see that something is changing and understand that energy is causing that. And typically, as with water and hydrogen and oxygen, specific forms of energy are required. So specifically, heat energy has to be used in order to transform hydrogen and oxygen into water. And specifically, electrical energy has to be used to change water back into hydrogen and oxygen. There are other forms of kinetic energy as well, which we'll study tangentially. We don't directly study them, but they'll come up as we go forward. Potential energy is a little harder to understand. And so today's discussion is primarily about kinetic energy. As you might have guessed from the title, right? Kinetic theory, that's what we're talking about. And the word molecular comes in there, you'll see in just a minute as well. Potential energy is something that we'll come to gradually over the course of this unit because it's a little harder to understand. At least in this context. But potential energy is energy that's stored, that's not actively changing anything right now. There's a couple examples of potential energy that you encounter all the time. So a battery is a good example of potential energy, right? The energy is there when it's just a battery, but it's not doing anything. And so it's just stored in the battery. Once I plug it into a device and turn the device on, then we have the kinetic energy. The energy is released from the battery in the form of kinetic energy, which is why the battery can run out, why the charge is drained from the battery. And then some batteries can be recharged again, so you store the energy back in there again. Another example of potential energy is food, right? We use food for our energy, right? If I have a sandwich, it's just sitting on the plate, nothing's changing, right? But there's energy in there. We know that because we can use that energy in our body. So the sandwich or food represents potential energy. It's energy that's stored. When we put it in our body and digest it, then it begins to be used. And it's used primarily to change the temperature of our body. Since we constantly lose heat to the environment around us, something that's discussed in your notes for homework, since we constantly lose heat to the environment around us, we have to constantly produce more heat. We have to constantly raise our temperature because our temperature wants to drop. And so that's mostly what the energy that we consume is used for. It's used for other things as well, including moving us around. But that means our food energy is being transformed from potential energy into kinetic energy. By the way, both forms, both of those examples could be chemical energy. The food energy is actually chemical energy, and some batteries use chemical energy as well. When you think about like traditional batteries, like a Duracell battery, those are actually chemical energy. There's a chemical reaction that produces the electricity. On the other hand, when you talk about some other types of batteries, like computer batteries, for example, it's a little bit more like electrical energy that's being stored. But technically, if you're storing electrical energy, purely electrical energy, it's actually called a capacitor instead of a battery. It's a different device. A battery stores chemical energy, generally speaking. All right, so that's the brief introduction to energy. Let's get more specific, and then feel free to stop me if you have any questions along the way. All right, so kinetic energy at its fundamental level is the energy of motion. If something is changing, then it's because something is moving somewhere. It just may not be as obvious in some cases. But for example, with electricity, right? Electricity actually moves through a wire and through an object. Something inside the atoms is actually moving to cause the electricity to flow through a wire or through a device. And so that flow is kinetic energy. So kinetic energy is the energy of motion. And if something is moving faster, it means it has more kinetic energy. Now, I should point out to you, and some of you may have already learned this in previous science classes, especially if you learned the formula for how to calculate kinetic energy, that mass is normally a part of kinetic energy as well. If an object has a larger mass, then it also has a higher kinetic energy. So for example, if we're going to analyze an automobile accident, a car crash, mass of the vehicles is a big part of the energy that's transferred between two objects. Obviously, if you're in a car and you get rear-ended by another car, it's different than if you get rear-ended by a tractor trailer, because the mass of the object has a lot to do with it. But speed has a bigger effect, right? That's true in auto crashes, but it's especially true in chemistry. When we talk about chemistry, we're talking about very, very small objects like atoms and molecules. So mass really doesn't have a big part in kinetic energy when we're talking about it in our context. That's one of the things that's different about chemistry compared to your other sciences, is we look at things at a very different scale. We're examining the world or the universe at a very small scale. And at that scale, mass is, as we say in science, negligible. We can just not worry about mass because the mass is so small that it has very little effect on the kinetic energy. And so when I say kinetic energy in chemistry class, I mean speed, basically. Speed is the dominant factor in kinetic energy for us. But I just want you to understand that if you go on to physics, that won't be the case. And mass is also a factor in kinetic energy for larger objects. And so kinetic theory has three components to it. And we could also call it kinetic molecular theory, because that's the word right here, particles, that brings that into play, right? So all matter consists of particles, which we could generically call molecules, but they could also be atoms, right? Those particles are in constant motion, and that's what I want to talk to you about today, or finish talking to you about today, which means that all matter has kinetic energy, right? Now, there will be another point that we'll add to that when we study gases later on, but I'll come around to that in just a moment, right? And so we're going to talk about the movement of particles in matter and how that relates particularly to states of matter, solids, liquids, and gases. All right, and that's the main topic for this week and next week as we go through this unit. First of all, we're going to be measuring temperature this week. So you've already measured mass and volume, two of the most important things that you can measure about any sample of matter. Another thing that we can measure is temperature. And then after that, there's actually only one other fundamental measurement that we can make, which we'll get to in Unit 3. Right, so I want to talk to you a little bit about temperature and make sure everybody understands what we're measuring, how we're measuring it, and why as we go through the lab. That's what you're going to be doing in person in your lab, measuring temperature of water as we boil it. And then later you're going to see temperature of a material as it turns from a liquid to a solid or freezes. All right, so when I heat something up, meaning add energy to it, and in particular, if we're talking about heat, we call it thermal energy. Thermal energy is the formal word for that. When I add heat to something, right, the particles absorb that energy. We'll talk about how they do that later on in the year. Right? Some of that energy is actually stored. So if I heat something up, some of it actually does become potential energy. It gets stored away by the particles. But for the most part, if I heat up a sample of matter, the particles move faster. And so their kinetic energy increases. Right? And then as you know, if I heat up something, its temperature increases. Right? So when I heat something, then the particles move faster. And when I heat something, the temperature increases. So what does temperature really measure? Well, temperature really measures the movement of the particles in a material. Temperature is actually kinetic energy. That's what temperature measures. Right? The hotter something is, the faster its particles are moving. It's not a measurement of like how fast the object might be moving. Like the temperature of a car doesn't tell me how fast it's moving down the highway. It's temperature is a measure of the movement of the particles inside that. We'll talk about how the particles can move a little bit later on. I have a visual for you that helps with that. So this is probably the most important single piece of information in this lecture here today. Right? This is the kind of thing that shows up on quizzes. Right? Temperature is defined as the average kinetic energy of the particles in whatever you're measuring. Now, temperature has some limitations. It's really easy to measure the temperature of a gas. If I put a thermometer outside, I'm measuring the kinetic energy of the air particles. Right? It's easy to measure the temperature of a liquid. Tomorrow, or this week, you'll put a thermometer into water, right? And you'll measure the kinetic energy of the water molecules. It's very hard to measure the temperature of a solid, and we'll get into why that is. And that's actually part of the lab. The second part is really challenging because of that, and that's why I'm going to do that by video rather than in person. All right, so temperature measures the average kinetic energy. And then as I said on the last slide, in chemistry, kinetic energy is really speed. We don't factor mass into our discussion. And so temperature, simply put, measures the speed at which the particles are moving. How does it? Well, particles collide with the thermometer. When I put a thermometer in something, the particles will bounce off of it as they're moving around. And then they transfer some of their energy to the thermometer when they collide. And then that energy is what causes the thermometer to respond, which means that when I put a thermometer in something, it actually affects the temperature of the object because it takes some of the energy away from the particles. It's important to understand that when I put anything into a sample of matter that I'm observing, it changes the sample, which is why we have to let a thermometer stay in something for a while before we can actually read it, right? If you take your own temperature, right, you're quite familiar with that concept, right? With an oral thermometer, you have to hold it in your mouth for a little while because when I first put it in there, it actually lowers the temperature of your mouth slightly. It takes energy away, and you got to wait for everything to come back up to temperature again, okay? Questions about the definition of temperature, which is the most important point here before I move on. Okay. And because temperature measures kinetic energy, we need a temperature scale that is reflective of kinetic energy. We need a temperature scale that if I look at that, I know exactly what that means about the kinetic energy of the subject. And the temperature scale that does that for us is called Kelvin. I don't know how many of you have encountered Kelvin temperature before. Usually it's about half of my students, roughly speaking. But the Kelvin temperature scale is the one that reflects the kinetic energy of the substance, which means that it's the best temperature scale for us to use in chemistry. And in some cases, it's the only one that works, and that'll be true in Unit 3. So that's why I'm previewing it right now, because you'll need to use it in the next unit. Kelvin temperature is related to Celsius temperature, and that's why we measure in Celsius most of the time. And then you need to convert it to Kelvin, which is actually quite easy. The reason why we can't use Celsius all the time is because Celsius has negative temperatures, right? But kinetic energy is never negative. And so a negative temperature doesn't really accurately reflect the kinetic energy of the substance. And it messes up calculations, and it also makes it harder to think about the calculation or about the kinetic energy. And so an enterprising scientist who happened to be a lord of English peerage known as Lord Kelvin, which is not his real name, that's his title, Lord Kelvin, decided, well, what if we just shift the Celsius scale up so there's no negative temperatures? Right? And so if you study Celsius, you find that it has a minimum temperature. There is a lowest temperature in the universe, and that lowest temperature in the Celsius scale is negative 273.15 degrees Celsius, which is a really awkward number, right? But that's something that we discovered as we've studied colder and colder temperatures in different forms of matter. Negative 273.15 degrees Celsius, which I'll discuss more in just a minute. So what Kelvin said was, well, what if we just make that 0 and just set that to 0? So essentially, Kelvin is just the Celsius scale shifted up 273.15 degrees. You don't have to remember the 0.15, right? But if I want to convert Celsius to Kelvin, then I need to add 273 to the Celsius temperature, which is pretty easy to do. And by the way, you don't have to memorize that. This is in your reference tables. I mentioned those earlier on today. If you don't have reference tables, make sure you get them. On the second page of the reference tables, this formula is in there so you can remember how to convert the temperatures. And so during the lab, right, you're going to measure Celsius, but then you're going to need to convert to Kelvin. And we'll especially need to do that in the third unit as well. So although they're different scales, they start from a different number, they actually have the same degrees along the way. So a change of 1 degree Celsius is the same as a change of 1 Kelvin, which weirdly, we don't call it degree Kelvin. It's just Kelvin, like meters, kelvins. So they actually, if you had a thermometer with Kelvin temperature, each little mark would be the same exact change as a thermometer with Celsius temperature. Each little mark would represent the same thing. It's just they start from a different bottom point. Kelvin starts from 0 and works its way up. That means all Kelvin temperatures are positive except for 0 itself, which we can never actually reach. And so since all Kelvin temperatures are positive, then they work very well when we're talking about kinetic energy, which is always positive. And so the Kelvin scale is very useful for that. If you've heard of the term absolute zero, that comes from the idea of 0 Kelvin. So that is the lowest temperature that we believe can exist in the universe, at least as we know it. There's always the possibility that we might discover something else along the way. 0 Kelvin, which is the same as negative 273.15 Celsius, can't actually be reached. So temperature approaches this limit asymptotically, if you know your math, meaning that it will continue on infinitely. It flattens out before it actually reaches that limit. So we can get really close to 0 Kelvin, but we can't actually get there, at least as far as we understand it right now. Absolute zero is not as wild a thing as some people think it is. It sounds fantastic. I've heard people say that they believe that like there's no movement of the particles at absolute zero. That's not really true. I've heard people say that like all matter would fall apart into its little pieces. Not true at all. Essentially at absolute zero, everything's a solid. That's a simplistic way of talking about it. Anything can be made solid if you cool it down enough. And at absolute zero, everything is a solid by definition. There's a little bit of a change in the behavior, but it's not as weird and strange as you think it is. I'll come back to that in just a minute and explain in more detail. All right, last thing, and this is a preview of something, or last thing for the notes. I have another, I have some visuals for you. This is a preview of what you're going to be doing in the lab. Right, so one of the things you're going to be, or really the only thing you're going to calculate during this lab is change in temperature. Right, and so we're going to be measuring the temperature over a period of time, and we're going to talk about the change in the temperature. Change has a symbol in science. Right, and again, change is associated with energy, right? So anytime you see this symbol that means change, you also should know that energy is automatically involved in some way. And we're talking about either gaining or losing energy in that substance. The symbol for change is the Greek letter delta, which looks like a triangle. That's the capital delta. And so change in temperature would be delta T. And a lot of times scientists will refer to it directly that way. I'll use that term some, although I'll spell it out as change in temperature during the lab as well. So when you see that, it means to subtract. Delta always means to do the same thing. It means to subtract. And specifically, we always subtract the final value minus the initial value, right? So as the temperature changes, you have a starting temperature and you have an ending temperature for whatever you're measuring, right? It'd be the ending temperature minus the starting temperature, always in that order, no matter what we put the delta in front of. It's always going to be final minus initial. The reason for that is delta doesn't just have an amount, like it's not just how much something changed, but it also tells us what direction. And if I subtract in the correct order, I will always get the correct sign. And so if delta T is positive, it means the temperature went up. And if delta T is negative, it means the temperature went down. And that's an important piece of information. It tells us whether energy is being added or whether energy is being removed from the substance. So that is something you're going to do, I think, 4 times during the lab, twice in part 1 and twice in part 2. And so just wanted to preview that a little bit. Does anybody have any questions about the concept and terms that I gave you here today before I end with a couple of visuals? Questions? All right, before I switch over to my animations, I want to remind you, if you're paying attention to the schedule, that you have homework, and that homework is another set of notes, right? It's posted on the same page as this set of notes, right? Which is on your, it's the lesson, Introduction to Kinetic Molecular Theory lesson. So sometime this week, you need to go and look at the next set of notes, which is States of Matter. There's no work on that yet. The work will be next week, but it reviews solid, liquid, and gas, and then fills in a few more important terms and a few more details, just to make sure everybody is operating from the same basic understanding. All right, so make sure that at some point you get the States of Matter notes covered. And I think you'll find them mostly basic, but there may be a few things in there that you hadn't picked up in the past or that we need to remember. All right, so then let me get to my animations. All right, so I want to give you a representation for what the particles kind of look like in a solid, a liquid, and a gas, as we're going to be talking about the 3 states of matter a lot this week. And our main focus is to talk about changes of state. So when I change from solid to liquid or liquid to gas or in the other direction. But it helps to have a visual for what each state looks like as we go forward. And then we'll fill in more details around this. This is what the particles in a solid might look like. Notice that they're very crowded together. Okay? And notice that there's very limited movement of the solid, which means that solids have low kinetic energy, right? And that makes sense if you think about it, since kinetic energy is temperature, solids exist at lower temperatures, right? If I take water and I lower the temperature, I can turn it into the solid form, ice, right? If I take solid water in the form of ice and warm it up, it'll melt and turn to liquid, at least if I warm it up enough. Okay? So solids have these particles, and notice that each particle inside the solid is locked in place, right? One particular particle can't move out of its place. They can't switch places. They can't move around each other. That means that solids have a rigid structure, right? Each particle has a place in that rigid structure. Within that place, though, it is moving, right? So even particles of solids, even things that appear to be very solid, even when they're very cold, particles can still move around. Even at absolute zero, particles can still move around. That's because there's three different kinds of movement. There's three different kinds of motion that contribute to kinetic energy. All three together become kinetic energy. There's vibration. You can see the particles are vibrating, right? Back and forth or up and down. There's rotation, right? The particles can actually rotate in their spot. That's not represented in this animation. And then the third kind of movement is called translation, which means moving from one place to another. And because I don't have these in the notes, that's a signal that you don't really have to know these. I'm just explaining because it helps to illustrate a point. Right? So solid particles have very little translation. They don't move around very much. They just vibrate and rotate in place. Right? This rigid structure means that solids have a defined shape. Right? A rock is not going to spontaneously change shape unless energy is involved somehow, right? So if I have a tennis ball, then that tennis ball is round and it's always gonna be round. If I put it in a bag, if I put it in a 2-liter bottle, it's always gonna be round. Solids have a defined shape and they also have a defined volume, right? The volume of a solid remains consistent. If I put a rock into a small graduated cylinder, or if I put it into a 2-liter bottle or a beaker, that rock has the same volume, no matter where I put it. So the volume and the shape of the solids are defined for them. Okay? Now, let's look at liquids. All right? This is what particles of a liquid might look like. They're moving a little bit more, right? Not vibrating necessarily a lot more or rotating more, but what they can do is they can translate. They can move from one place to another. The particles can move past each other. They can flow, in other words. That's a very simple word for the fact that liquids can flow. The particles can move around each other. That means liquids do not have a defined shape, right? So water doesn't come with a shape unless it's in the solid form, ice, right? Liquid water is shaped by its container. Whatever I put the water in, then that's the shape the water will have. If I put the water in a square container, like an ice cube tray, then it'll end up square shaped. If I put the water in a round container, like a soda bottle, and then freeze it, it'll end up round. So liquid water takes the shape of its container. However, liquid water does still have a defined volume, right? If I take a 1-liter bottle of water, pour it into a 2-liter bottle, I still have 1 liter of water, right? It's not going to spread out and become suddenly 2 liters. So water has a defined volume, but does not have a defined shape. And that's the thing that makes it different from solids. Now notice that the particles are still crowded together in the solid state. Okay? And that's important to understand. How many of you have heard in the past that changing from solid to liquid or liquid to gas, changing state, has something to do with the space between the particles? When we talk about solids and liquids, that's not true, right? And I know some people have learned that in the past, but it's not true about solids and liquids. The space between the particles has nothing to do with the change between solid and liquid. In fact, in water, the liquid particles are actually closer together than they are in the solid state, right? So the space between the particles has nothing to do with solids or liquids. It does for gases, but not solids and liquids. It's the freedom to move. that makes a difference between solids and liquids. Liquid particles are free to move around, and solids particles are not. And that's something that we'll come back to a little bit later on. So a lot of times I ask students, and we don't have time for me to ask you, but a lot of times I ask students, which two states of matter are the most similar? And people often say liquids and gases, because they can both flow. In reality, solids and liquids are very similar to each other, and gases are radically different. And that's why we're actually going to put off studying gases until Unit 3. They get their own unit because they're so different from solids and liquids. But you can see what I mean when we look at this animation, right? This looks nothing like what solids and liquids look like. The particles are spread out. There's more space than there is particles. And this is why I was telling you the other day that space is closer to us than we think, not just in a literal sense like outer space, but anytime you're around a gas like air, most of that gas is actually empty space between the particles, right? The volume of a gas, this is weird to think of, but the volume of a gas is mostly the volume of space between the particles. The volume of a liquid or a solid is the volume of the particles because there's very little space between them. Still a little bit, but very small. Now, just to illustrate the point earlier, if I heat up the particles, right, they move faster. Right? And then if I allow that in a gas, they will actually spread out, right? And so that means a gas does not have a defined volume either, right? So gas can change volume and gas can change shape as well. Liquids can only change shape, but they always keep their volume. And solids cannot change shape or volume, right? And so that's one way that we can distinguish between the states of matter. Right, now all that was a quick introduction. There's more detail on this in the next set of notes, right? So just giving you a visual that you can use when you go through those notes to picture things as we're talking about it. And we'll dig more into this as we go forward. But for the meantime, does anybody have any questions? If not, then we're done. Have a good day, and I will see you in lab this week.
Thank you.
You're welcome.
Thank you. Thank you.